Space is open to us now, and our eagerness to share its meaning is not governed by the efforts of others. We go into space because whatever mankind must undertake, free men must fully share. I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
Before 1970, Americans will land an odd-looking spacecraft on the surface of the moon, step out, and walk across the lunar landscape. The government agency meeting the challenge of the manned lunar landing program, as well as other space explorations, is the National Aeronautics and Space Administration. One of NASA's major installations devoted to achieving the goals of the nation's space programs is the John F. Kennedy Space Center, launch site for the Apollo Saturn V. From here, under direction of a government industry launch team, astronauts will begin their journey to the moon. For the first time, the free world had undertaken development of an operational spaceport. Its design and construction was one of the nation's greatest engineering challenges. The immensity of the project required the joint efforts of the National Aeronautics and Space Administration and the Department of Defense, as well as the technical skills of American industry. An operational spaceport, rather than a research and development facility, was conceived by Dr. Kurt Debus and his staff of NASA engineers. Plans for the mobile concept of launching huge space vehicles had been developed throughout years of experience in NASA's launch operations. The mobile concept differed greatly from the methods used to launch earlier space vehicles. At Cape Kennedy, assembly and checkout of the Saturn I rockets on the launch pad occupied the facility for extensive periods of time. It also exposed the launch vehicle to the damaging effects of the sun, corrosive salt air, wind, and rain. Large service structures which provided platforms for checkout operations were moved to and from the pedestal on rails. When the rocket was ready for flight, the countdown was conducted from a blockhouse near the pad.
Range launch clearance. Clear to launch. Range ready, switch on. Switch on. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
For the much larger Apollo Saturn V, a new procedure of servicing and launching the giant rocket was developed. This new mobile concept calls for assembly of the moon rocket in the controlled environment of a building. Then, with the rocket mounted on a mobile launcher, a huge tracked vehicle transfers it to a distant pad ready for launch. A service structure is moved to the pad and placed next to the rocket for final servicing. In the Launch Control Center, instruments monitor all components of the huge vehicle throughout assembly and launch preparations. Prior to launch, the service structure is removed and liftoff occurs, vacating the pad for the next rocket. This plan was the basis for design of Launch Complex 39, a new operational facility for launching large space vehicles at a more rapid rate. Approximately 1,500 engineers worked on design of the required buildings and launch equipment. Their output on drawings and specifications weighed over 100 tons. In 1960, a study group considered 8 locations for the manned lunar landing launch site, including Hawaii, Christmas Island, locations in Texas and Georgia, and the Cape area in Florida. 88,000 acres of land on Merritt Island, just west of the already established Cape, was the logical choice. This vast expanse of land would provide the required safety zone for launching huge space vehicles, including room for expansion if necessary. This site was not only the least expensive to acquire, but most important, the location permitted continued use of the tracking stations of the Air Force Eastern Test Range. NASA assigned the U.S. Army Corps of Engineers the responsibility of design and construction supervision for the spaceport facilities. However, private industry performed most of the design work and all of the construction work under contract to the Corps of Engineers. In mid-1961, the Corps initiated acquisition of land on Merritt Island, paving the way for early phases of construction. A rail spur was laid from the Florida mainland to Merritt Island, and construction materials for the huge spaceport soon traveled over it. Thousands of men, representing numerous construction trades, came from every corner of the nation to build the varied facilities of the Space Center. Huge bulldozers and earth movers rolled across the coastal wilderness, clearing everything in their paths. Road builders began construction on primary roads connecting the new launch area to the Florida mainland on the west and the Cape on the east. Secondary roads were built to areas where facilities were to be constructed. 2 causeways were dredged up, one crossing the Indian River, connecting the spaceport with Highway US 1 on the mainland. The other causeway, across the Banana River, provided access between the Cape and the Space Center. The lifelines of a community carrying electricity and telephone communication soon threaded the landscape. Pump stations were built and pipelines were laid for water supply. Utility poles were raised and a network of lines formed a trail from power plants on the mainland. Then, the vital link of telephone communications was installed.
Good afternoon, John F. Kennedy Space Center.
As contractors prepared for construction of the vehicle assembly building at the Space Center, thirsty dredges pumped over 1 million cubic yards of waterborne fill onto the site. A 9-mile access channel up the Banana River to the VAB site was the source of the fill material. This channel is used to transport the first stage of the Saturn V to an unloading ramp at the VAB. To support the vehicle assembly building, a 52-story skyscraper which covers 8 acres, sand-filled tubular steel pilings were driven 160 feet to bedrock. Total length of the pilings, if placed end to end, would stretch 126 miles. The pilings were then capped with concrete, not only to support the building, but also to serve as an anchor, a safeguard against tropical hurricanes. A tight construction schedule, thousands of tons of structural and reinforcing steel fabricated in plants throughout the country, and 500 iron workers required the use of computers to make sure that the right steel members, necessary equipment, and supplies would be on the job at the right time. Computer-coated columns and beams were spread across the sandy terrain like toothpicks, awaiting use as the steel framework began to rise. Some of the columns have rolled section cores heavier than any ever rolled before. As the steel was raised by derricks atop its framework and by cranes reaching 250 feet into the Florida sky, bolting crews, almost indiscernible amidst the steel web, used the biggest impact wrenches available to connect the steel with more than 1 million high-strength bolts. The 57,000 tons of structural steel in the framework, enough to manufacture 30,000 automobiles, was pre-coated with an application of zinc to prevent corrosion by the salt air sweeping in from the Atlantic Ocean. In April 1965, the vehicle assembly building was topped out by placing a 4-ton steel beam at the 525-foot level. The beam was autographed prior to ceremony by government and contractor personnel at the Space Center. Completing the basic construction of the vehicle assembly building, siding crews enclosed the structure with aluminum panels. To facilitate the work, a 3-level cage enclosed on 3 sides was developed. The cage hung from temporary rails attached to a steel girt just above the working area. The metal panels were rolled into position on inner rails and then bolted to the side of the building. In all, over 23 acres of siding were installed. Inside the building, where the Apollo Saturn V is assembled and prepared for flight, work was completed first on the low bay area. In this section of the building, engineers designed cell-like work platforms 34 feet in diameter on each side of a transfer aisle. These platforms enable technicians to service the 2nd and 3rd stages at necessary levels. A bridge-type crane with a lifting capacity of 175 tons was installed in the transfer aisle. The crane lifts the upper stages and transports them through the 670-foot transfer aisle to the high bay area. 2 more bridge-type cranes installed in the high bay area then lift the stages gently and lower them for mating. These cranes, with a capacity of 250 tons, have a hook height of 46 stories above the floor. There are 4 high bays in which Apollo Saturn V rockets can be assembled and checked. For each of these high bays, work platforms were assembled outside the building and moved inside for mounting. These platforms, as big as whole buildings 3 stories high, were installed on the sides of the bays. The platforms can be adjusted up and down and moved in and out like suspended file drawers. They meet with each other to form even larger structures which encircle the space vehicles for checkout. 21 high-speed elevators were installed at strategic locations throughout the VAB to transport personnel and equipment to various floor levels of the building. Some of these elevators are capable of traveling up to 11 feet per second. Because of the height of the Apollo Saturn V, the vehicle assembly building has 4 of the largest doors in the world. Each door is built in the shape of an inverted T, reaching 450 feet high. These door openings are large enough for such structures as the United Nations building and Chicago's Wrigley Tower to pass through. At the time of its construction, this building, in terms of cubic volume, was the largest in the world. The nerve center for space activities at Launch Complex 39 is the Launch Control Center. This four-story reinforced concrete structure was built adjacent to the VAB for the purpose of controlling pre-launch and launch operations of the Apollo Saturn V. The most important areas of this facility are 4 firing rooms, which correspond to the 4 high bays in the VAB. Each of these rooms is 2 stories high, and each is designed to house 470 monitors and consoles for assembly, checkout, and launch activities. To give launch crews a picture window view of the launch pads, 3 quarter-inch thick laminated glass windows were installed on the east side. These windows, made of tinted glass, allow only 28% of the light to penetrate, thus filtering out unwanted rays which cause glare and heat. The windows are protected by vertical power-operated louvers, which can be opened or closed as desired. The Launch Control Center received the 1965 Architectural Award for the Industrial Design of the Year. When the Apollo Saturn V is ready for flight, the vehicle is mounted on a mobile launch platform. NASA engineers supervised design and construction of 3 of these mobile launchers at a site near the VAB. The base of the launcher, 2 stories tall and half the size of a football field, is built of steel plate girders. Inside, areas were provided for various equipment required for vehicle checkout and launch. Steel plating up to 1 inch thick was used for the launch deck, from which the rocket will lift off. A large opening was placed in the deck to allow the rocket's flames to pass through and away from the launcher. A steel tower was built at one end of the launcher platform to carry fuel, electricity, pneumatic, and communications cables to various stages of the vehicle. The 45-story launch tower and its Apollo Saturn V cargo are moved from the VAB to the launch pads by a transporter designed by Space Center engineers. 2 of these large land vehicles were built at a special parking area near the mobile launchers. At each corner of the vehicle were assembled double tracks, 10 feet high and 40 feet long. On these tracks, the transporter creeps along at 1 mile per hour. A diesel-electric system mounted under the decking develops 5,600 horsepower. 2 diesel engines supply energy to electric motors at each corner, which in turn deliver motive power to the huge tracks. These 5.5 million-pound transporters, equal in size to a baseball diamond, are capable of slipping under a mobile launcher, lifting the platform with hydraulic jacks, and moving the launcher to and from the VAB. On the day of the moon journey, astronauts will ride an elevator to the upper level of the launch tower and enter their spacecraft through one of these steel arms, which reach out for contact with the rocket. Each arm is designed to swing away from the rocket at liftoff. Completely outfitted, the mobile launcher stands 445 feet tall and weighs 10.5 million pounds. To support the transporter and its cargo, engineers designed a special road called the Crawlerway. It is equal in width to an 8-lane parkway. Like a causeway, it was built by dredging and placing hundreds of thousands of cubic yards of hydraulic sand fill across the swamplands and open water sections of the Banana River. And finally, smooth river rock was chosen as a surface covering, which offered less steering resistance for the transporter and a more firm and even distribution of the load. At a site midway between the VAB and the launch pads, a mobile service structure was erected. Built of steel, the service tower was put together in pre-assembled sections. These sections were welded at the plants, bolted while on the ground, and hoisted to position by high-reaching cranes. To minimize weight, all flooring of the tower consisted of aluminum honeycomb panels. This material not only reduced weight, but its structural rigidity assured stability of the floors. The forward side of the mobile service structure was equipped with 5 clamshell platforms, which completely surround the rocket while at the launch pad, providing access to several levels of the vehicle and spacecraft for final servicing. This tower also is moved to and from the launch pads by the transporter, even in winds up to 45 miles per hour. In 1963, the site chosen for Complex 39's launch pads was for the most part underwater. It was a parcel of swampland near the Atlantic Ocean just north of Cape Kennedy. The desolate scene rapidly changed, however, when huge dredges deposited almost 5 million cubic yards of waterborne fill material onto the launch sites. Soon, an 80-foot mountain of surcharge was shaped in the form of a truncated pyramid to consolidate the subgrade beneath. The surcharge was then removed to its permanent level, and the launch pads took shape. Lattice works of reinforcement steel soon rose above the silvery sand. Workmen climbed about the net-like array, tying and welding the steel bars to fortify the launching stand. With reinforcement in place, a convoy of trucks delivered 68,000 cubic yards of concrete, enough to build 1,700 average homes. A flame trench, surfaced with heat-resisting bricks, was built through the pad center. By way of this trench, the 2,000-degree flames from the rocket are directed away from the hard stand. For the myriad of electrical connections and test equipment required for checkout and launch operations, workmen installed 8,400 miles of wiring. This is comparable to the amount needed to wire the homes for a city of 135,000 people. Under the sloping shoulders, designers provided engineering areas for control systems, electrical rooms, and high-pressure gas storage facilities. Surrounding the hard stand, 900,000-gallon tanks were built to service the rocket with liquid hydrogen and RP-1 fuels, liquid oxygen, and liquid nitrogen. These massive forms of concrete, towers of steel, and giant buildings received the American Society of Civil Engineers Award for Outstanding Engineering Achievement for 1966. 5 miles south of Complex 39, an industrial complex, comprising more than 50 structures, housing administrative, engineering, and laboratory facilities, was built to support the manned lunar landing program. In fact, there are enough facilities in this area to support a small city. This administrative and engineering community is a concentration of management and support offices. Spacecraft checkout facilities where manned vehicles pass rigid tests prior to flight. An instrumentation complex that gathers and stores vital data from launch activities. And maintenance and repair shops. Appreciating the value of natural resources, NASA developed a land management program at the nation's spaceport. Hundreds of acres of grove land purchased from owners were leased back to them so that production could continue. Citrus trees still blossom, and oranges and grapefruit are harvested. A game refuge was established, and during the season, hunters are allowed into the marshlands. Ocean beaches to the north of Kennedy Space Center are open to the public the year around, except at launch times. And on tour days, thousands visit the spaceport to view these specialized facilities. Few people in this nation, and indeed the world, have not wondered at the prospect of those 3 Americans who will one day journey from this Earth on what will be our first trip to the moon. As the eventful day of the moon journey approaches, other rockets, such as the Saturn 1B, are testing the lunar spacecraft. And astronauts train for the distant voyage by flying long-duration orbits of the Earth. Man has taken a giant step toward the stars with the construction of the spaceport. His new equipment, tools, and buildings, standing as monuments of the space age, have brought him ever closer to the realm of the universe. He stands today on the threshold of a rendezvous with destiny.